Hi friends, myself Shiv Kumar, studying in GM University in the fifth sem in IML branch. So, so here I am. I am here to explain the assignment, and the topic is evaluate and propose improvements in pathfinding algorithm, A-star search versus greedy based search. This means the topic compares two algorithms, A-star and greedy based for search, and looks for ways to improve them. And next slide. So coming to the introduction part, here the first point, pathfinding algorithms are core components of artificial intelligence and robotics that determine the optimal path between 2 points that are nodes in a graph or grid. So this means these algorithms help find the best route from one place to another on map or grids. So what to say means pathfinding algorithms are used in AI and robotics to find the best route one point to from one point to another point. And next point, these algorithms are crucial in navigation system, game, AI, logistics, and robotics. Both A-star and greedy-based first search belongs to the family of informed search algorithms, which use heuristic functions to guide search toward the global efficiency. A-star and greedy-based first search are heuristic-based search algorithms. So this means they are used in many fields like GPS, games, and delivery and planning robots. So A-star and greedy based first search uses guess about how far a node is from the goal to decide where to search next. And next, the goal, evaluate their efficiency, heuristic impact, and propose improvement. So this means the project wants to check how fast and good these algorithms are, how the heuristic affects them, and suggest ways to make them better. Next, coming to the next slide. So coming to the objectives, first point, to understand and explain the working principles of A-star and greedy based first search algorithms. So this means this explains how A-star and greedy based first search actually works. And next, to compare both algorithms in terms of time complexity, space complexity, and path complexity. So this means it compares how fast they run, how much memory they need, and how good the paths they find are. And next point, to analyze the role of heuristic functions in determining algorithm performance. So this means look at how the heuristic changes speed and outcomes. And next point, to identify practical applications where each algorithm perform best. So this means it points out real world cases where one algorithm is better choice than the other. And uh, next point, to propose innovative improvements for enhancing scalability, speed, accuracy in pathfinding. So this means it suggests new methods to make the algorithm faster, work on bigger problems, or be more accurate. And next point, to evaluate how hybrid or adaptive techniques can improve real-world pathfinding performance. So this means it checks if combines methods are adapting strategies during search makes it makes things better in practice. And next, coming to the next slide. So this is the working principle of A-star search. So in the first point, it combines uniform cost search and greedy first search. It means A-star mixes careful cost tracking of uniform cost search with the goal-directed guessing of greedy search. And next, evaluation function. F of n is equal to g of n plus h of n. So it means A star picks nodes uses a score f of n that adds the cost so far g of n and the guessed remaining cost that is h. And next, where g of n it is equal to actual cost from the start node to the current node. It means g of n is how much it costs to get to this node from the start node. And next, h of n heuristic estimates of the cost from the current node to the goal. It means h of n is our guess of how much it will cost from this node to reach the goal. And next, f of n is equal to estimated total cost of path through node n. So it means f of n is the total estimated cost if we go through this node, the sum of what we have spent and what we expect to spend. And coming to the next slide. So the next slide is working principle of greedy best first search. So it mainly focus only on heuristic value. It means greedy best first search makes decision only based on how close a node seems to be to the goal. It doesn't care about the total cost so far. And next, evaluation function is equal to f of n is equal to h of n. It means the function uses to decide which node to explore next. It just the heuristic value, that is h of n, which estimates the distance from the current node to the goal. And next step, these are the algorithm steps. First one, start from the initial nodes. So it begins the search from the starting point. And next, use a priority queue ordered by the smallest heuristic value h of n. It stores all possible nodes in a list, that is priority queue, where nodes with smaller h of n come first. And next, it selects next point, select the node with the lowest h of n and expand it. So choose the most promising node closest to goal according to the heuristic and explore its neighbors. And next, continue until the goal is reached or no nodes are left. It means keep doing this until you find the goal or you run out of nodes to explore. And next slide. So in this slide is it is a performance comparison. So in the first row, from the first column, there are the aspects, and next column it is a star algorithm, and next the greedy best first search. So in evaluation function, a star is G of n plus h of n. It means A star uses both cost so far and estimated cost to goal. Here, greedy best first search uses only the heuristic, that is h of n. And next, optimal solution. Here, A star always finds the best path if the heuristic is correct. And next, greedy best first search may not find the best path. And next, time complexity. A star takes more time depending on how deep the goal is. And next, greedy based first search can be faster, but sometimes explores more useless nodes. And next, space complexity. So ESTAR uses more memory because it stores many paths. And next, greedy based first search usually uses less, but it depends on the heuristic. And next, speed. ESTAR is slower but reliable. And next, greedy based first search is faster but riskier. And next, the path quality. So A star gives the best path, and next, greedy best first search gives a path that may not be the best. And next slide. So in this slide, impact of heuristic functions. So this means heuristic estimates distance to goal. It means a heuristic tells how far a node is from the goal. It's just a guess. And next, common heuristics. So these are the common heuristic, that is Manhattan distance, and next Euclidean distance, and Capsule distance. So Manhattan distance. It means it steps needed moving only up, down, left, and right. And next Euclidean distance. It is a straight line. And next. Um, Chebyshev distance, it distance if you can move diagonally as well. And next, impact on A star. So a stronger but admissible heuristic reduces search space drastically. It means a good heuristic makes A star search fewer nodes and reach the goal faster. And for example, a user Manhattan distance. And next, impact on greedy best first search. So greedy best first search performance depends solely on the heuristic. Since greedy best first search only looks at h of n, a good heuristic makes it work well, a bad one makes it fail. And next, a poor heuristic leads to wrong direction and longer search time. It means if the heuristic misleads, greedy best first search wastes time exploring the wrong paths. And next, in dynamic environments, heuristic adaptation reweighting improves efficiency. It means in changing situations, adjusting the heuristic can help the algorithm perform better. And next slide. So in this slide, we look into the practical use cases. So first one, GPS navigation. So A star GPS systems like Google Maps uses the A star algorithm to find the shortest and most efficient route. So here A star ensures the result is optimal, which is important for real world navigation. And next, game AI. So A star in games, characters use A star to move smoothly and realistically between points. So and next, it avoids obstacles and create believable movement paths. And next, robot navigation, A star. So robots often uses A star since it is meaning safety critical. So meaning the robot must choose the best path to avoid collisions or damage. And next, web crawlers. It uses greedy based for search. So use it for fast exploration of web pages, and greedy based for search helps find new link quickly without worrying about the perfect path. And next, fifth one, search engines. So it uses a greedy bus for search. So search engines like Google use a similar idea to focus on most relevant results first. So it's faster and more practical when dealing with huge data. So coming to the next slide. So these are the proposed improvements. So improvements in A star. First one, weighted A star, adds a weight factor to the heuristic. It helps balance between a speed and accuracy. Next, adaptive A star. So adjusts the heuristic dynamically based on the environment. It means it useful in changing or unpredictable surroundings. And next, bidirectional A star runs the search from both start goal start and goal points. So this reduces search time by meeting in the middle. And next, hierarchical A star, it splits large maps into clusters and searches within small regions first. So this makes an algorithm faster on large scale problems. And next, fifth one, learning based heuristics. So uses AI or machine learning to predict better heuristic values. So it means the algorithm learns which directions are promising. And next, improving in greedy based for search. So first one, adaptive heuristic updating. Updates the heuristic during search using feedback from explored nodes. And next, helps avoiding getting stuck in wrong paths. And next, hybrid S star or greedy best first algorithm combines both algorithms, mixes A star accuracy with greedy best versus speed, uses a tenable way to adjust between cost and heuristic. And next, multi-resolution search. Start searching with large grid cells, then switches to smaller ones near obstacles for precision. This saves times while keeping accuracy. And next, anytime grid is search, so quickly finds an initial path and improves it over time as more time is available. So useful for real time systems that can't wait for a perfect answer. Next slide. So coming to the conclusion part, A star and greedy best first search are both powerful heuristic algorithms with distinct advantages. So it means both are used for pathfinding but serve different needs. So A star gives perfect rules, greedy best search gives fast results. So A star guarantees optimally and completeness, making it ideal for critical applications requiring precise results. So A star always finds the best solution if one exists perfect for tasks like GPS and robotics. And next, greedy best first greedy best first search, although less accurate, excels in speed and low memory use for real-time or exploration scenarios. So greedy best first search is best when speed matters more than perfection, like in web crawling or quick searches. And next, the future of pathfinding lies in hybrid adaptive systems. The next generation of algorithm will combine ideas like heuristic learning and dynamic weighting and parallel computation. The heuristic learning, it is AI based improvements, and it's dynamic weighting, that is adjusting important factors, and parallel computation, it uses multiple processes. This will make algorithms work efficiently in large and real world environments. So this is about our my presentation. Thank you, Shilpaman, for giving the opportunity to present my assignment and the idea. So thank you.